Number 6. This is a dynamics problem. We're looking at acceleration, the change in velocity, because the speed is going down. And we know forces. We have gravity and we have a normal force. So are these equal and opposite? Well, if they were, the acceleration would be 0 and this would be in equilibrium. But the velocity is going downward and slowing down. So which one of these is bigger? If it was going down at a constant rate, it'd be in equilibrium and these would be the same. But it's slowing down. So something must be pulling it upwards, so this force must be greater than the force of gravity because the acceleration is up. Now how about the force that I exert on the object and the force that it exerts on me? How many forces do we have there? One force, a repulsive force between the two, and between my hand and the box, it's equal and opposite. Number 7 is kinematics. Is it possible to have acceleration without velocity? And so can velocity be 0 and still be changing? And we see this all the time. When this marker reaches the top, it's still being accelerated at negative 10 meters per second squared, but the velocity is at 0. Right? Here's the elevation. It goes up very fast with a high velocity. Here, the velocity is 0. But it's still changing. The acceleration is negative. Can I have velocity without acceleration? That's just constant velocity. Okay, so we have Ratu Toka is sitting under a tree by the side of the river where the river is flowing at 4 meters per second and E.C. Kelly is in that river. So this is the speed of E.C. Kelly according to the land. Ratu Toka is not moving. And I'm pointed across the river at 4 meters per second, but this water is also moving at 4 meters per second in this direction. And so Ratu Toka would see me move this way, and he would see my velocity like this. So he would see the velocity of Pete equal, let's get an axis. This is in the positive x direction, this is the y direction. He would see my velocity as 4 meters per second in the x plus 4 meters per second in the y. And in order to find that absolute value, you just take the square root of 2 times 4 meters per second, so we're talking about 5.6 meters per second. Ratu Toka also sees E.C. Kelly moving in this direction at 4 meters per second, and he sees himself as motionless. Now E.C. Kelly is floating on the river, he sees himself as motionless. He would say, oh, I'm not moving, but Ratu Toka is moving in this direction at 4 meters per second, and Pete is moving in this direction, right? He's floating along, he just sees me moving at 4 meters per second in the positive y direction. Okay, now me, I'm moving across the river where I'm flowing down. No, I say I'm not moving. I'm not moving, but I see E.C. Kelly going in this direction at 4 meters per second, right? I'm sitting in a boat, and the land is moving like this, and E.C. Kelly's moving like this. Excellent. Okay, so he's moving in this direction, according to me, and I look and I see Ratu Toka. Ratu Toka is coming closer. He's moving at 4 meters per second, and he's moving in this direction at 4 meters per second. So the general rule, if you want to know the math, is we don't see ourselves moving at all. And so whatever velocity we have to take off of ourselves, we take off of everybody else. And so with E.C. Kelly, if we go into Ratu Toka's reference frame, it's a reference frame of Ratu Toka, how he sees the world. He sees E.C. Kelly moving in this direction at 4 meters per second. Now when we jump into that reference frame, we have to add a negative 4 meters per second in the x direction to everything. To him, now he's 0, Ratu Toka is moving 4 meters per second in that direction, and Pete's just going straight up. And Pete, according to Ratu Toka, has this velocity. And so if we want to put ourselves in this reference frame, we subtract that velocity off from me, I'm stationary, from him, now instead of moving forward, he's moving down, and from Ratu Toka, he is moving in this direction.